Okay, now it's recording. So on problem 3, where you had that, I'm hearing this hissing. Like, I thought I have the sound off on one of my devices. Anyway, okay. A whole lot of people tried to turn this into a Taylor series in R and Z. So they started taking derivatives with respect to R and Z. But I never said that R is small or that Z is small. I said that D is small. So we should have, and yes, I'm aware that there's supposed to be a Q over 4 pi. I'm leaving that out. What we should have is that V of R is that V is roughly V of R, Z, and then D equals 0, plus partial V, partial D, D equals 0 times D, plus partial V, partial squared V, partial D squared, D equals 0 times D squared over 2. So all those derivatives with respect to R and Z were completely missing the point. When we ask for a Taylor series in a particular variable, that doesn't mean that you start taking derivatives with respect to all of the other variables. We're treating all of those other variables as fixed. What we're looking at is, we're just looking at derivatives with respect to the thing that we're going to expand in. Any questions on that?
Yes, Professor. So when we do the Taylor expansion of this with respect to D at D equals 0, we don't plug in 0 for R or Z. It's just D equals 0, correct?
Correct. R and Z are whatever they are. If I've got a function of 10 variables and I ask you to expand in one of them, we don't make all of the others 0. We don't even make that variable 0 until after we've calculated the derivatives. Another thing that some people have done, leave D in. I'm going to take a much simpler function. Let's say we have e to the minus x squared. All right, well, this is e to the minus x squared, which is 1 plus minus x squared plus minus x squared, whole thing squared over 2 factorial. That's how I would think of it. I would think of it as e to the u with u equals x squared. But what some people did is they said, okay, or actually, we'll stick with that. They said, or they might say, the derivative of e to the minus x squared with respect to x is minus 2x e to the minus x squared. So they would say that e to the minus x squared is roughly e to the minus x squared minus 2x e to the minus x squared times x, because they say here's the function and here's the derivative. So we'll take the derivative and then we'll multiply it by x. Well, no. What you should be doing is plugging in x equals 0 here and plugging in x equals 0 here, and then finding the second derivative and plugging in x equals 0 there. Questions on this? Okay, let's pick up with linear algebra. So last time I was talking about why linear algebra matters in physics. And I was saying that it's because we can use matrices to represent linear relationships between quantities. For instance, polarization density could be written as chi xx. I should write polarization density x component, chi xx ex plus chi xy ey plus chi x z e z. This just expresses the fact that the polarization density, the density of polarization along the x direction is a linear function of the three components of the electric field. And in general, we could write similar things for PY and PZ, and then we could say that P is equal to the chi matrix operating on the E vector. Now, people come up with all sorts of notations for matrices. Sometimes they will put little double squiggles under them. Sometimes they'll do them in bold print. That's a little bit harder to do when writing by hand. We're going to have to often just do it by context. Expressing things with context in math is nothing new. The Babylonians didn't have a zero, and so they expect you to figure out from context whether they were talking about the ones place, the 60s place, the 3600s place, and yes, they did base 60 math. They expected you to figure out from context whether they were doing things after the decimal point. So this is nothing new in math. This is how people have always learned math. And if people could somehow learn math that way thousands of years ago, then you should be able to learn math the same way today, expressing certain things with context. All right. The other reason why linear algebra and vector spaces matter so much in physics is because it provides a convenient set of tools for breaking down functions into pieces. Remember, we talked about, say, cubic polynomials. If I have some function defined between x equals -1 and x equals +1, I could express this in terms of a set of polynomials, P0 of x, P1 of x, P2 of x, P3 of x, and so forth. And I could write this as f of x equals the sum from j equals 0 to whatever limit of approximation I want to say, j equals 0 to j max of cj p sub j of x, and then the integral of f of x squared dx from -1 to 1 just turned out to be the sum of cj squared. And so we go from expressing a function as some complicated expression, with a whole bunch of x's and various factors in it, to just expressing a function as an array of coefficients, C0, C1, C2, etc. And then when we do that, calculating the squared integral becomes a matter of multiplying this array by itself, or more formally taking that array, having a row vector of complex conjugates of coefficients dotted with a column vector of coefficients. Any questions so far? And there's no rule that we have to stick to functions between -1 and +1. We could talk about functions defined in other domains. We could talk about functions defined as sums from j equals -infinity to infinity, or let's say j looks too much like I. You'll see why I care about that in a moment. Cm e to the I m phi. That would be another perfectly valid way of writing things down. And again, we would just care about an array of coefficients. Now you may be thinking we can't deal with an infinite array. So then we replace this with sum from m equals -m max to plus m max of cm e to the I m phi. And again, we just have to talk about an array of coefficients. All right. Given that we can represent functions as arrays of coefficients and do all the things that we would do with, or column vectors, technically I should call them, do all the things with functions that we would do with column vectors, let's talk more about linear algebra. And again, I'm not going to attempt to teach an entire semester of linear algebra in 3 or 4 lectures. I'm refreshing the key points. I'm hoping that with a refresher you will remember things. Just as the Babylonians were able to do math in context, the Babylonians were able to learn things and then remember them. That's how you would get a job as a mathematician in Babylon. You would first learn math, and then you would remember it so that you could go and work as a mathematician doing surveying or calendars or navigation or accounting. Babylonians were capable of remembering things. I'm going to make the generous assumption that modern Americans can as well. So in linear algebra, we talk about vector spaces. And a vector space, very generally, is just a set of objects with a few simple operations. Closure under addition. Closure is just a fancy way of saying that if we take 2 elements of the set and combine them, then we get another element of that set of objects. So that A plus B is in the vector space. And addition, now this means, this is a little bit subtle. If I look at, say, the set of all quadratic polynomials, if I look at the set of all quadratic polynomials in X, so ax squared plus bx plus c, a1x squared plus b1x plus c1 plus a2x squared plus b2x plus c2. Well, that's clearly just another quadratic polynomial. That's equal to a1 plus a2 x squared plus b1 plus b2 x plus c1 plus c2. There, we have another quadratic polynomial. It's in that set. Why am I harping on this? Because it means that all the ideas that we develop in linear algebra can be used to describe things like this. They can be applied to polynomials. They could be applied to sums of sines and cosines. If we had the set of all combos of sine kx, cosine kx, sine 2kx, and cosine of 2kx, then if I had a1 sine kx plus b1 cosine kx plus c1 sine 2kx plus d1 cosine of 2kx. There, I've just defined a function in terms of 4 coefficients, right? Just said, hey, here's a function that's defined in terms of these 4 coefficients. And I could add to it another function defined in terms of the same 4 coefficients. And I could add them together, and I get another function of that form. All the math that we're developing here applies to that, and it applies to the 4 coefficients that define it. Now, some people then say, hey, what if I want to take the set of all quadratics with a equals 1. So all polynomials of the form x squared plus bx plus c. So it says I want to look at all polynomials of that form. Then what would happen if we were to add two polynomials of that form? Do we get back another polynomial of that form? No, we don't. Because if I were to add two polynomials like that, I get 2x squared plus b1 plus b2 x plus c1 plus c2. That's not of the original form. The original form had just x squared. The new one has 2x squared. So we have to be a little bit careful. All of the math that we're developing right now only works, it's only useful if we are talking about a set of objects that we can add up together and get more objects from that same set. It's not something that we have to harp on a lot, but it comes up every now and then. It's one of those facts that you should file away in the back of your mind. I like to say that there's a time and a place for thinking about math as a physicist. How do we use this? And that's great day in and day out. And not worrying about all those proofs that your math professors were harping on with the epsilons and deltas and the proof that for any epsilon greater than 0, there exists some delta such that yada, yada. That's great until you have to do something a little bit different. You find that you want to use this math to solve a problem that has a discontinuity in it. And then suddenly those epsilon and delta proofs matter. You say, what do you mean they matter? I just want to apply the math to this problem. Yeah, but it all breaks down for that problem. So it's good to file away a lot of these technicalities because you never know when they'll come up. There is actually a place for that stuff that your math professors blather on about. All right, well, let's talk about, there are a few other axioms of a vector space. They also have closure under scalar multiplication. And usually are scalar, which means that if A is in the vector space and B is 2 and S1, S2 are scalar numbers, S1A plus S2B is in the space, we will usually say that S is from the complex plane. There are cases where S is some other type of scalar. We're not going to deal with those. Okay, so far, obviously we could apply this to polynomials. Sums of sinusoids, vectors of the form we've been dealing with before, column vectors, C1, C2, Cn, row vectors, C1, C2, Cn. We can apply it to matrices. People think of matrices as being different from vectors, and in some ways they are. You can multiply them in ways that we don't normally do with vectors. But if I were to consider the set of all matrices of the form A, B, C, D, I could write those as A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. All right, so these form a vector space. You may be thinking, well, does that just apply to 2 by 2 matrices? No, I could do it with 3 by 3, 4 by 4, or 2 by 3, or 2 by 17, or 15 by 1000, by whatever. Matrices can form vector spaces. Usually for a vector space, we work with something called a basis. That's just a set of vectors. Everything else is written in terms of. Right? So for the vectors that you're used to, x hat, y hat, z hat. Or for those who prefer, I hat, j hat, k hat. Those aren't the only ones. We could have decided, we've talked about this a lot, we could always work with tilted axes. Axes tilted with respect to the x, y, and z directions, and this could be e hat 3. There's lots of ways that we could write down a basis. It could be convenient to write it in terms of some other set of axes. In solid state physics, studying crystalline materials, often the atoms of a crystal are not laid out in some nice uniform square array, but are instead in some sort of hexagonal array. And I'm drawing these pretty badly right now. So then we might have axes that are tilted at 60 degrees or some other angle. Basis vectors could be like this. It could be column vectors. Each column vector has just one non-zero element, but it doesn't have to be that way. Here's a set of column vectors that we could use as a basis. And then 1, 0, minus 1, 0. And then finally 0, 1, 0, minus 1. We could use those as a basis because we could write any other vector as some linear combination of these. The key thing is that if the set e hat 1, e hat 2, e hat n is a basis, then any vector v can be written as the sum of cj e hat j. Questions?
Yeah, I have a question. So in order for these vectors to form a basis, they all have to be linearly independent from each other, correct?
That's correct.
Okay, thank you.
They have to be linearly independent, which means that you could have, say, x and 1 plus x as a basis for linear functions, because I can't write x in terms of 1 plus x. You might be thinking, sure I can. X is just 1 plus x minus 1. Well, yeah, that is true, but I can't write x in terms of 1 plus, I can't write x is not equal to some coefficient times 1 plus x. They're linearly independent. I can't start off with 1 plus x and then only do things that involve multiplication by scalars and get the function x out. But a plus bx is equal to a times 1 plus x plus b minus a times x. Here's a coefficient. Here's a coefficient. Hopefully that idea of linear independence is sounding familiar from linear algebra. It's something that your linear algebra professor probably harped on a lot. It matters because we need to have things that are independent of each other. It's like trying to write a vector in 3 dimensions using only vectors in the xy plane. Okay, if I had a bunch of vectors in the xy plane, I could write vectors, I could write other vectors in the xy plane in terms of them, but then somebody wants a vector that reaches out into the 3rd dimension, and I've got nothing pointing in that 3rd dimension to build it out of. Okay, if you think of basis vectors as building blocks, then you're trying to build something that sticks out in this direction. Well, you need pieces that already stick out in that direction so that you can add them up. That's what a linear combination is. If there's nothing pointing in that direction, there's nothing to add up in there. That's why linear independence is so important. And of course, bases aren't just sets of coefficients. A basis could be 1x, x squared, x cubed. Or it could be p0 of x, p1 of x, p2 of x, p3 of x, if you think back to those Legendre polynomials from last time. Or it could be the set of all sine of mx, cosine of mx. It all depends on what type of vector space we're trying to work in. All right. Matrices. Matrices are also called linear operators or linear transformations. And for our purposes, the whole idea of a linear transformation is that it's something that mixes up elements of vectors. L of u, if u was equal to the sum of ci times e hat I, then some linear operator acting on u gives us the sum over all of the coefficients of L sub I, ci, L sub ij, ci, e hat j. Right, what it does is it takes elements of vectors and mixes them up. And yeah, it takes elements of vectors and mixes them up. And matrices do that. If I've got the matrix A, B, C, D acting on the vector V1, V2, I get, well, matrix multiplication is row dotted with column. So I get A V1 plus B V2, and then row dot column C V1 plus D V2. All right, and so I started with an old vector, and I get a new vector. And the elements of the new vector are mixes of elements of the old vector. Anytime you've got something where your input is a vector, your output is a vector, it involves some linear formulas, that the new vector is some linear formula involving the old vector, we can represent it as a matrix, and it's just mixing them up. We talked last time about, say, polarization in electric field. That's not the only example. Something we do all the time is we do calculus on functions. So let's say we've got f of x is equal to C0 times P0 plus C1 P1 plus C2 P2 plus C3 P3. Partial f partial x will be, well, P0 was a constant. So 0 times C0 P0 plus C1 partial P1 by partial x plus C2 partial P2 by partial x plus C3 partial P3 by partial x. And I'm going to share my other screen right now. In the Mathematica file that I posted last week, we defined these functions. We could take derivatives of these functions. The derivative of P3 would be some quadratic function. So it would be some function that I could write in terms of P2 and P0. And you may be thinking, well, wait, it's a quadratic polynomial, and P2 is a quadratic polynomial. Couldn't I just say that the derivative of P3 is P2? But let's look carefully at the derivative of P3. In the derivative of P3, I've got that one of these coefficients is minus 5 times the other coefficient. Whereas in P2, one of these coefficients is minus 3 times the other coefficient. You see, you've got a -1 here and a +3 there. So I could say that the coefficient of x squared is minus 3 times the coefficient of 1, or x to the 0. Whereas here I've got that the coefficient of x squared is 15 and the coefficient of x to the 0 is -3. So this coefficient is -5 times -3, or +15. So it's not like the derivative of P3 is just proportional to P2, all right? These are different polynomials. Questions on that? Let's figure out what that is. All right, let's figure out how to break that into pieces. We know that any vector can be written as the sum of v dot e hat j e hat j. Remember how for vectors in three-dimensional space, ax was just a dotted with x hat. Well, that's true in n-dimensional space. And how did we define a dot product of two functions last time? Anybody reach back into their memory and think, how did we define a dot product of two functions last time? Oh, I see in the chat there was some discussion of how much math the Babylonians had to remember. The good news is they didn't have to remember 60 unique symbols their method of constructing digits 1 through 59 was kind of logical. The symbol for 11 looked a lot like the symbol for 21, just with something added to it that would clearly indicate it's 10 bigger, which looked a lot like the symbol for 31, except the 31 had something added to it that made it look like it's 10 bigger. So they didn't actually have to remember nearly as many things as you think, but they did remember things. Okay, so somebody said that the dot product is, no, it's not that. How do we define the dot product of functions? Not discrete vectors.
Yeah, sorry, that was my mistake. Yeah, it throws away the vector, right? So then it's just the sum of the x components with the x components plus the y components plus the z components. Two vectors, and they multiply.
Okay, so yeah, if we've got things defined in terms of a number of discrete components, but how did we define things for functions in the first place?
Was it the magnitude multiplied times the cosine of theta?
No, because we don't know what the angle is between functions. If I've got two functions defined on the interval from -1 to +1, if I want to find the inner product of two functions f and g, it was the integral from -1 to +1.
It's the functions multiplied with each other.
What?
Isn't it the functions multiplied with each other?
And then what?
Oh, and then you integrate it from, yeah, those bounds.
Yep. So if I say that e hat 0 is p0, e hat 1 is p1, e hat 2 is p, I should really be writing these as functions of x. Then what I could do is I could say that f of x is the sum of cj, pj of x, and the inner product of, say, p2 of x with f of x would just be the integral of p2 of x, f of x, and that would give me c2. And likewise, and if our f of x here is partial p3 by partial x, then all we have to do is, I'm going to try to share my screen. All right, so there's the derivative of p3 of x. It's this thing. I want to figure out how to write that in terms of p0 and p2. So I'm going to say that f of x is defined as that. And then I'm going to say that c0 is equal to the integral of f of x times p0 of x, x from -1 to 1. And c1 is the integral of f of x times p1 of x from -1 to 1. And lo and behold, that's 0, because the even function up here, and this is an even function, when multiplied by an odd function gives us, multiplied by an odd function, P1, gives us an odd function. And the integral of an odd function from -1 to +1 is just 0. And C2 is the integral of f of x, oops. Oops, C2 equals that. And C3 is the integral of f of x times P3 of x, x from -1 to 1. All right, so what we've just done is we have just figured out how to take the function, how to take the derivative of P3 and express that in terms of all of the other vectors. So what I can say is that I'm going to put this on my other, I'm going to write this out by hand.
Dr. Small,
Yeah.
is there a reason why you put an asterisk on f of x in that first inner product?
Because it should be the complex conjugate, but everything that I was dealing with here was real, so I got a little bit sloppy with it. If I'm only dealing with real numbers, I tend to get a little bit sloppy, much like I tend to use contractions in informal speech, but I wouldn't usually put a contraction into formal academic writing. Or when I'm speaking informally, I might pause like, you know, this, but I wouldn't put like, you know, into formal writing usually, unless it was for a very specific rhetorical point. So what did we find? We found that the derivative of P3 of x with respect to x was equal to the square root of 7 times P0 plus square root of 35 times P2. All right? So what we could say is that if we could somehow write the derivative as a matrix, all right? If we were to write this derivative as a matrix, and we start off with this input. This is P3 of x. It may not look like it, because it looks just like a column of numbers instead of looking like that cubic polynomial. But this is totally a matrix, but this is totally P3 of x, because it's saying we don't have any C0, P0, we don't have P1, we don't have P2, but we do have P3, okay? That is a way of writing P3 of x. Then when we take the derivative, what do we get out? Well, we get square root of 7 P0. We don't get any P1. We get square root of 35 P2, and we don't get any P3. So that when we take the derivative of this polynomial, we get out the sum of these two functions, the weighted sum of these two functions. Any questions? Somebody must have a question.
Are we going to find that matrix that would take the derivative of P3?
We'll start finding that matrix. I'm going to let you finish it on the homework, not this Wednesday's homework, but the following Wednesday. But we could start constructing that matrix. What we immediately know is we know some of the entries in this matrix, okay? If I were to call these matrices, these entries D01, D02, sorry, D00, blah. Let me just start from the beginning here. Why can't I erase there? I'm going to call these D00, D01, D02, D03, D10, D11, D12, D13, D20, D21, D22, D23, and D30, D31, D32, D33. Well, let's see here. We have just figured out one of the columns. We have just figured out this column. Because when we take this, say, this first row and operate on this vector, well, I get D00 times 0. Doesn't really matter what the value of D00 was because the answer is 0 no matter what. Plus D01 times 0. Again, doesn't matter what D01 was. Plus D02 times 0. Doesn't really matter what D02 was. Plus D03 times 1. Likewise, when we have this next row dotted with this column, well, the first 3 entries in that row, we don't really know what they were. We just know they got multiplied by 0. But we do know that the last entry in this row over here got multiplied by 1, and yet our answer was 0. So what can we conclude about D13?
It equals 0.
Yep, it's got to be 0. And then likewise, this row, well, the first 3 entries we multiplied by all of these, we got 0. So we don't really actually know what any of these entries should have been. But then we took D23 and multiplied it by 1, and we got square root of 35. So we can immediately say that this matrix is of the form D00, D01, D02, square root of 7, D10, D11, D120, D20, D21, D22, square root of 35, D30, D31, D32, 0. We know 4 of these. And if I wanted to get the next 4, which we won't do, but if I wanted to get the next 4, then what I would do is I would take the derivative of, say, P2. And that's going to be something to get the next column. Then I would dot that function with my 4 basis functions. And what I would finally get out is 4 matrix elements. Any questions?
So are you saying that this matrix, when we apply it to a vector, gives us the derivative of that vector?
I'm saying no, it doesn't really. You should be very careful. This column vector represents a function. I'm saying that we could represent a function with a column vector. And then we could represent the derivative of that function with another column vector. Our function would be a combination of 4 polynomials. the derivative of that function would be some other combination of those same 4 polynomials. All right. The matrix tells us, or represents, the process of going from the 4 polynomials in the function to some new combo of polynomials. Does that make sense?
Yeah, so it's a change of bases matrix, correct?
I wouldn't call it a change of basis because it's still a combination of the same 4 polynomials. All right, we're still working in that basis of those 4 polynomials. We're just taking a different combination of them.
Okay, yeah, that makes sense.
All
Thank
right,
you.
all of what we've done so far has been to motivate the use of matrices in physics. Now let's just run through basic properties of matrices and matrix multiplication. One, the single most important aspect of matrix multiplication, the aspect of it that drives a lot of the weirdness in quantum mechanics, is that it is non-commutative. To wit, let's consider 0, 1, 1, 0. Most of what we're going to do for the rest of this chapter is going to involve 2 by 2 matrices, although there will be a little bit of 3 by 3. Let's consider this process. This matrix, by the way, has a name. We're going to see the law is called sigma x. This is called sigma z. These names come from quantum mechanics. For now, they're just names. Let's multiply them. Row dotted with column. So 0 times 1 plus 1 times 0, 0. Row dotted with column. 0 times 0 plus 1 times -1 is -1. Row dotted with column. 1 times 1 plus 0 times 0. Row dotted with column. 1 times 0 plus 0 times -1. All right. That's this product, sigma x, sigma z. Now let's reverse it. Row dotted with column. 0. Well, that starts off looking the same. Row dotted with column. 1 times 1 plus 0 times 0. 1. Row dotted with column. 0 times 0 plus -1 times 1. Row dotted with column. 0 times 1 plus -1 times 0. Now in this case, reversing the order multiplied by -1, that is not always the case, all right? What is often the case is this, that sigma x, sigma z is not equal to sigma z, sigma x. That is almost always the case. AB is usually not BA. There are exceptions, but that's the thing about them. They are exceptions. They are not the rule. Here's another property of matrices. You could take things that are non-zero, multiply them by each other, and get eventually 0. All right, let's consider 0, 0, 0, 1, 0, 0, 0, 1, 0, multiplied by itself. 0, 0, 0, 1, 0, 0, 0, 1, 0. Row dotted with column. This row dotted with any column will be 0, so we just get a bunch of zeros across the top. This row dotted with any column, well, yeah, there are non-zero entries in this row and this row, but they're always going to be multiplied by 0. And there's a non-zero thing here, but it's always multiplied by a top element. Then finally, this row dotted with this column gives us a 1. When we dot it with the other two columns, we get 0, 0. So if we call this a squared, now let's do a cubed. So we're going to take this matrix, 0, 0, 0, 1, 0, 0, 0, 1, 0, and multiply it by the original matrix, because this row dotted with any column is 0. This row dotted with any column will also be 0. And then finally, we take this row, multiply it by a column. And yeah, there's a non-zero element in this row, but that non-zero element always gets multiplied by the middle row. Do you see anything non-zero in the middle row? I don't. So here we've got a case where A is non-zero. A cubed is 0. Matrices are very different from the numbers we're used to. Now you may be thinking, well, does that mean that everything raised to a power is 0? Definitely not. Raise this to any power you want it to. Multiply it by itself a whole bunch of times.
I have a quick question, if you don't mind.
Charles?
Yeah, the matrix where you did a times, where you got a cubed, second matrix, is the one supposed to be at in the bottom in the middle, or is it supposed to be in the bottom left?
Oh, shoot, you're right. The good news, such as it is that it won't matter. My bad. Because the only thing that ever this is a non-zero element, but it's always going to be the third column that gets multiplied by this third row, and everything in the third column is 0. But yes, thank you for catching that. All right, so I was saying that we can have matrices that are non-zero, but if we raise them to some higher power, we get 0. That's not always true. For instance, sigma z, if I took sigma z squared, I'm going to get 1, 0, 0 minus 1 times 1, 0, 0 minus 1. Row dotted with column, I get a 1. Row dotted with column, I get a 0. Row dotted with column, I get a 0. And then row dotted with column. Now, yes, I have a minus 1 here, but I have a minus 1 there. And I multiply minus 1 by minus 1, and I get 1. And this has a special name. It's called big I for identity. Little I equals imaginary. Big I is identity. So the identity matrix is basically the matrix version of 1. Whereas little I is the square root of -1. Now, I squared this matrix. If I were to take sigma z cubed, I would have sigma z multiplied by the identity matrix, which is just sigma z. And if I were to take sigma z to the fourth, I would have sigma z times sigma z. And what did we establish that sigma z times sigma z is?
The identity matrix.
Yep. So no matter what we do, I have a matrix here that I can raise to any power I want, and I'll never get 0. Whereas I have a matrix here that I can raise to a high enough power and get 0. What I want you to take away from this is not try to memorize this matrix cubed with 0, this other matrix cubed is itself. What I want you to take away is that matrix multiplication does not obey the same rules as, that matrix multiplication does not obey the same rules as multiplication of numbers. Here's another one just to show you how weird it can get. 0, 1, 0, 1. B squared would be 0, 1, 0, 1 times 0, 1, 0, 1. That would be row dotted with column, 0. Row dotted with column, 0 times 1 plus 1 times 1, hey, that's 1. Row dotted with column, 0. 0 times 1 plus 1 times 1, 1. So here we've got b squared equals b, even though b is not equal to 0 and b is not equal to the identity. If we tried to, in regular algebra, with regular numbers, solve the equation x squared equals x, we get x squared minus x equals 0 equals x times x minus 1. X is 0 or 1. With matrices, all bets are off. Any questions on what I did there? Well, I said to you that matrices don't always commute, but sometimes they do. Here's a pair of matrices. 1/2 √3 over 2 minus √3 over 2, 1/2 multiplied by 1/2 minus √3 over 2, √3 over 2, 1/2. 1/2 times 1/2 is 1/4. √3 over 2 times √3 over 2 is 3/4. So that's going to be 1. 1/2 times minus √3 over 2 is minus √3 over 4. √3 over 2 times 1/2 is plus √3 over 4. Hey, those go to 0. Minus √3 over 2 times 1/2 is minus √3 over 4. And why did I put a minus sign there? That should just be 1/2. 1/2 times √3 over 2 is √3 over 4. That goes to 0. And then minus √3 over 2 times minus √3 over 2, we get 3 over 4. And 1/2 times 1/2 is 1/4. So we get 1, 0, 0, 1. And I'm not going to go through all the tedious multiplication, but we would have gotten the exact same thing if we had reversed the order. So sometimes they commute. Any questions on what I did?
I have a question.
Yeah.
Does the fact that we get the identity matrix have to do with anything with the fact that like 1 over 2 and √3 over 2 are all like the the products of identity triangles, like the cosines of stuff?
Well, it turns out that if I were to call this matrix R, this would be the transpose of R. And R transpose R in this case equals identity.
Oh, okay.
Some of you are about to say, hey, does that mean that like anytime I multiply a matrix by I get the identity? Absolutely not. Just in this case. Matrices commute with their own inverses. For now, I'm not doing general rules. What I'm trying to illustrate to you is the complexities of matrix multiplication. So if you take nothing else away, take away that you can't make the same assumptions in matrix multiplication that you make in multiplication of numbers. Any questions before we go on and start defining special kinds of matrices and rules for them? Okay, then what I'm going to do for the rest of today is I'm going to start introducing some more matrix concepts, which I hope you have seen before. I consider all of this review. On Wednesday, we will talk about eigenvalues and diagonalization, which is the real structure of matrix problems. And again, I think it's something that your linear algebra professors have done. I'm going to show you how physicists think about that structure. And then on Friday in the activity, you will calculate the eigenvalues and eigenvectors of a whole bunch of matrices. I'll have you do some of it by hand and then most of it in Mathematica. I want you to see the patterns. The reality is that people nowadays use computers to do almost all of their matrix inversion and almost all of their eigenvalue calculations. What I want you to see is the structure. I want you to see, hey, what happens if we change this one element in this matrix? How do the eigenvalues and eigenvectors change? Hey, what happens if I have two matrices that have the same general structure to them or follow the same pattern? Do their eigenvalues also follow that pattern? Let's find out. I want you to develop some intuition for that. So first we motivate linear algebra, then we run through all the terminology, then we actually see what is the structure that emerges when we try different kinds of matrices having different properties. So you should have already done some reading on this when practicing for it. Let's talk about the transpose. Transpose means that you flip it around diagonally. All right, if A was equal to 1, 2, 3, 4, A transpose would be 1, 3, 2, 4. Meaning that you just swapped things across the diagonal. And if B was 1, 2, 3, 4, 5, 6, 7, 8, 9, then B transpose would be, well, the diagonals don't change, 1, 5, 9. The off diagonals get switched, 2 and 4, 3 and 7, 8 and 6. Right? That's a transpose. More generally, if the elements of A are called Aij, then the elements of A transpose, the Ij element of A transpose is the Ji element of A, where you've got row number, column number. So you've got the element in row I, column J of matrix A. Well, in matrix A transpose, the element in row I, column J is whatever was in row J, column I. I realize that that's that's a tricky thing to memorize. I just always visualize it with the flip. Right? That's the only way I know how to do it. It's a flipped matrix, so it is a very educationally progressive matrix. A rule of transposes, which I'm not going to derive, is that AB transpose is B transpose A transpose. If I've got a product and I want to transpose the product, that's the same as transposing the things that we multiplied and reversing the orders. Now, often, we can also transpose more than just square matrices. If I've got a column vector, transpose produces a row vector. And finally, in physics, we often deal with transposing and complex conjugation together. And so then we talk about something called a dagger, which when written by hand looks like a little t, a lowercase t instead of an uppercase t. When written in textbooks, they use a symbol that looks more like a dagger. A dagger is A transposed and complex conjugated. Many of the most important matrices in physics are Hermitian, which means that A dagger equals A. It's not at all obvious, but it turns out that you'll learn this in quantum mechanics, that most of the kinds of matrices that you have to deal with in quantum mechanics, not all of them, but most of them, are Hermitian. So here are some examples of Hermitian matrices. We can write, well, let's see here. Sigma x is clearly Hermitian because if we flip around, if we flip it, we get the same thing back. And since it's real, taking the complex conjugate doesn't change anything. I is Hermitian.
Dr. Schnall,
Yeah.
would that be A dagger equals A transpose for a real matrix?
For a Hermitian matrix.
On the
If this is true,
oh, okay, sorry.
if A dagger equals A, then A is Hermitian. It turns out that a lot of the matrices that are used to solve the wave equation, people do approximate solutions to the wave equation because most of the situations where we want to solve the wave equation, we can't do it by hand. Whenever you try to approximate the wave equation, you wind up with Hermitian matrices. So in optics and acoustics, Hermitian matrices are important. Sigma z is Hermitian. And then there's something called sigma y. And of course, if I flip that, if I take the transpose, sigma y transpose is 0i negative I. So sigma y transpose is not the same, and sigma y conjugate is not the same. But what if I do both operations at once in either order? Then I get the same thing back. All right, I'm going to stop there. Next time we're going to talk about some more properties of matrices and types of matrices, and we'll start talking about eigenvalues. And we are going to be running behind, but we will cut into the time for vector differential calculus. I don't think vector differential calculus needs as much time as vector integral calculus. So we'll shorten vector differential calculus and we'll be okay. I'll have my usual office hours. I'll stick around for a few minutes. Otherwise, I'll see you Wednesday.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Yeah,
Have a
thanks.
good day,
Dr.
Dr.
Mal.
Mal.
Any questions, gentlemen? All right, Nathan, Dylan, if you don't have any questions, I'm going to log out.
Okay.